strictly less than epsilon. Just try so far. You just need to cleverly choose. But समझ आ रहा है? Because this shows that the distance between lim2 minus L is less than epsilon by 2 equal. Epsilon by 2 is obviously strictly less than 1. Breaking this strictness will be just of yours thinking. ठीक है? Lim n के लिए खुद argument देना है. Think about it. How can I do the limit? It's just going to be exactly opposite. So you have this, and you're going to have inferior here, and then you take the supremum. It's always going to be precisely the same. ठीक है? Let's quickly do the converse. Converse में क्या होगा assumption? So if in the converse we're going to say that lim sup and lim n are equal to what else? I need to prove that. So conversely, suppose, just think about it that how does this result follows from the previous result that we proved? Just take that statement out and just think about it that why this result should be true in the light of what we proved previously, not this result, but the result before basically this. So L is, we say that lim sup of AL is L, lim n of AN is also L, n goes to infinity. Our objective is, okay.
So one side's inequality will be from L's lim flip, and one side's.
So we proved from previous result, we know that for epsilon positive, there exists n1 and n2 such that the distance between lim sup, okay, minus L is less than epsilon for all n bigger than or equal to n1. And the distance between lim n minus L is bigger than minus epsilon. Okay? And this is so for all n, for all n bigger than or equal to n2 actually.
Now still the maximum.
Okay, we got that. And then, if I take n to be what the maximum of n1 and n2, and since both of these numbers are basically true, what this is going to show up. That's what. नहीं. So यहाँ जो है an आता है, वो से n आता है. उसमें हम ग्राफ
Clear.
So you combine both basically, you get like an minus L is smaller than epsilon, and bigger than minus epsilon for all bigger than or equal to capital. Okay. So, ठीक है? So next I would like to prove a result which is kind of a miraculous result, very interesting result. So this result is important itself because it gives you kind of a characterization of convergence in the terms of limb soup and limb soup. So you can characterize it's kind of an equivalence condition. I know it's a bit boring, but it's a payoff thing. Here's a very interesting result. But you will also find a generalization of this result basically in Rudin, in the sense of relationship. But our argument is going to be essentially same. So result is this. So let AN be a bounded sequence. So it's a bounded sequence. Okay. And S be the set of all subsequential limits actually. S be the set of all subsequential limits. Can a bounded sequence have more than one convergent subsequence? Although Ness's theorem that there is at least one. So just think of it. My question is this: if I have been given a bounded sequence, why I'm saying that? Because Bolzano-Wester's theorem that says that there must be at least one, convergent subsequence of the sequence, basically, original sequence. Then this S must be singleton actually.
He says at least.
At least one.
So this.
But how we can using the same Bolzano-Wester's theorem determine that there are going to be more actually? Just think about it. You have a sequence which is bounded, so it is a convergent subsequence. That convergent subsequence is itself bounded. So that convergent subsequence has a further subsequence which is going to be convergent. Lots of, but that subsequence of subsequence is also going to be the subsequence of the main sequence actually. Anyway, so let S be the set of all subsequential limits of AN. Okay, so it's a collection of. So imagine that AN has lots of convergent subsequences, and we have put there all of their limits in this set. This part. Further, then directly I can say, then this set S must be contained in this number, in this interval M capital, where M is limit of AN, M goes to infinity, and the capital L is limit of convolution. Agreed? Okay. Do you think it's something interesting? Just think about it. If you have a bounded sequence and you want to have convergent subsequences, their limits are always going to stay between limits and limits of the sequence. So it can't go beyond actually limits and limits. That's a set where all limits are sitting. Is it an interesting information about sequence? Huh? Is it necessary that every bounded sequence should converge? It's not necessary. But it must have convergent subsequences. Those subsequences are going to converge to some numbers. We are saying that all those numbers you can find in this interval. Okay. Another thing.
Oh, now करेंगे इससे
We should say that this n capital N must be both subsequent. In other words, these two elements must be in N. It must be in this set S. This set S should be contained. So in other words, all of the limits are going to be between M and N. And these M and small m and capital M must be in N. Must be in S. So that's what we would like to quickly prove. Huh? Proper subset. Obviously, proper subset. होना चाहिए proper subset. And then equal basically. I don't think so. Because you can have. But this could be equal. Why? Because imagine the sequence is bounded and convergent. Then everything is basically. So this S is going to be singleton. So M is going to be equal to M. And all of the subsequences are going to converge to the same M. In other words, this S must be singleton. It's just going to contain one element. Because all subsequences are going to converge to the same number. Okay? So you can have equalities. So let's quickly think about the proof. Here's the proof there. Okay? So these are the results, beta, that you have to keep in your permanent vocab activity. Okay? All these results are very important for the rest of your life. So here's the proof. So let's begin by showing that this M and M belongs to S. And then take an arbitrary element from S and show that it must be in this interval. That's what we do. Let's think about that why this M should be an S. So what is your guess? What is the meaning of this actually? M belongs to S. What is the meaning of this? So in other words, we need to show that there exists a subsequence of this sequence L which converges to this M. Because then it is going to incite difference. Now what is that subsequence?
The supremums.
Sequence of
Supremums. No. Sequence supremums.
So by one of the previous results, not the previous, but the result that we proved before the last result, okay, which we also use there, in which we say that an minus L is less than epsilon for all n bigger than or equal to n, which is bigger than minus epsilon for infinity many. importing towards that. So using that, so for epsilon positive, there exists N1 such that AK, okay, AK is less than N plus epsilon for all K bigger than or equal to. For all K bigger than or equal to. N1 agreed? So it's like and minus L is less than epsilon for all N. And we also shown that for N1 bigger than N2, N1 smaller than N2 smaller than N3, so on and so forth, A and K is bigger than M minus epsilon. Okay. So that was the two parts basically of that. So this must be true for all K, and this must be true for infinity many N Ks. Okay. So if I combine these both, what I'm going to have? A and K is bigger than M minus epsilon and M plus epsilon. Okay. For all and K bigger than or equal to what? Bigger than or equal to what? अच्छा ये कितनों के लिए true है? So this is true for all K belongs to M. So you can always find N1, 3, right? This is true for all N. So when this is going to be true, basically, you tell me the number. I'm trying to say N के लिए true तो वो N के क्या होना चाहिए? किससे बड़ा होगा?
In one cell.
So should be bigger than or equal to what? Okay, so you take any N after N1, you know that this relation is going to be true. And if this is the case, that's what you wanted actually. ये चाहिए था that N K minus M is between minus epsilon and plus epsilon. So here the sequence will converge basically. ठीक है? ये भाई साहब क्यों होंगे यहाँ पर थिंग्स फॉर योरसेल्फ. So I'm leaving this data for आपके सोचने के लिए और आप सोचने वाली चीजें हैं. सर के टॉप पर एग्जाम है. ठीक है. You go through that data. It's going to be singleton actually. Even M and capital M are going to be same. Because we proved just previously that if a sequence is converging to L, then the lim sup and lim f are going to be F. And we have also proved that all subsequences also converge to basically same. So in other words, what follows from here is that if a sequence is convergent, then the set of all subsequential limit is going to be singleton, which is going to be that limit. Okay? So next I would like to prove is that S is contained in, so in other words, I'll pick an element from S which is going to be the limit of some subsequence, and I'm going to show that that limit must be between this smaller m and capital M. Can't go beyond that. Okay. So like X is an S. So if it is an X, so I'm going to say there exists A and K a subsequence of the sequence such that A and K goes to X as K goes to infinity. That's what we mean. Okay. You see a relationship between this inequality and this convergence. What is the relationship between them? Is there a relationship? And if there is, what?
Có thể cái khi chúng ta cái đây chúng ta phải đi làm điều này và điều này cái cái này mà đều
Cái model sequence.
gọi là
Is there a relationship between
M model sequence.
this and this?
cái này
Call this equation number star. Call this equation number. Call this star. I mean, if you see what we are saying, then as this is true for all AKs, for all k bigger than or equal to n. So this AK must contain basically this ANK as well actually. So in other words, in these AKs, the terms of these sequences are going to appear actually. If you make this K sufficiently large, maybe this will not be N1, maybe something else. But if you make this K sufficiently large, so this inequality is also going to be true for almost after some time almost all terms of this sequence. The AK is the sequence. And K is a subsequence of the sequence. So if this is true for all sequence, then it is going to be true for all subsequences as well. But not maybe with the same instant, maybe with a different instant, but such kind of inequality is going to hold for all subsequences. Okay? So what my point is this, that as An is less than n plus epsilon for sufficiently large n, so this is true for sufficiently large n. So we're going to say that Ank is going to be less than m plus epsilon, for sufficiently large.
NK.
Exactly. Sufficiently large. And what would be that, instant? We don't know, but it is going to happen. If this is happening for sequence, then this must happen for sequence. Agree? And what would be the next thing? What does this imply? If this is true for, so we just basically proved previously one result, that if one sequence is smaller than other sequence, then the limit is going to be also smaller. So in other words, if all of this sequence is smaller than this number, then the limit is also going to be smaller. In other words, we can say that x is less than or equal to, and it could be equal to basically 5. There's nothing that changes. Like that. So since if the epsilon is arbitrary, this epsilon is completely arbitrary. No matter what epsilon you choose, no matter how small you choose, this means that this x is always going to be smaller than epsilon. If you proved an inequality for an arbitrary epsilon, that means that this x is going to be always smaller than or equal to 2. Okay? No matter how hard you try, this x cannot go to this. And what do you think that the argument for the other side of argument should be? So it's going to be something similar. That so as an is bigger than m minus epsilon. Okay. So an is going to be bigger than small m minus epsilon. Okay. And then you're going to say that x is going to be bigger than or equal to. So by similar arguments. So when you will prove its counterpart, actually, for lemons, you're going to have similar inequality and similar conclusion. So using similar inequality, you get by similar argument. We can show that this x must be bigger than or equal to m. That's what we wanted. What is the x is between the small m and m. Okay. What is the beauty of this result is that it tells you that if you have a bounded sequence, okay, then all subsequential limits of that bounded sequence should be between basically lim sup and lim n. Okay. That's what it says. And obviously, the corollary of this result is going to be that if a sequence is convergent, then this S is singular. Yes.
इसमें जो सब सीक्वेंस होगी हमारे पास इंडिपेंडेंट होंगी वो नॉर्मल से होगी या
Subsequences.
जो हम सीरियसली करेंगे वो आपको की डिसर्टिफिकेशन
Bounded होगी.
इनकम और वो जो सबसेक्शन है उनकी जो मतलब इंटरसेक्शन मिलेगा वो नॉट इक्वल टू मतलब कुछ कॉमन आएगा नहीं है
In subsequences, can you have something common within subsequences? May or may not have. You can have a sequence and two subsequences which don't have anything common. For example, this thing. I'm taking 1 over n and 1 over 2n and 1 over 2n minus 1 and 1 over 4n. That's the sequence and these three are subsequences of this. Are these two going to have anything in common? Because it's going to be 1 half, 1 fourth, 1 sixth, 1 eighth, and this is going to be 1/3, 1/5, 1 seventh. There's nothing common. But you can find a common between these two. So 1 half, 1 fourth, 1 fourth, 1 eighth. So it may or may not match. 12 minus 1. You can have subsequences.
लेकिन अगर सारी subsequence की बात करें हो सकता है कि सारी subsequence
Size of sequences. That's not possible. For a sequence, how many subsequences we can have? Uncountable, not infinite. The more proper word is that you can even run a combinatorial argument and you can show that there are uncountable subsequences of sequences. नहीं हो भी सकता है नहीं भी तो I can take two sequences where last to last you have one you have countable disjoint subsequences. The answer is yes. Just like you keep on taking subsequence of this sequence and you keep on taking subsequences from within this sequence, they are always going to be described. I would like to end this discussion on lim sup and limits On the last result, Sukkur one, which is key. Oh, much easier. Something really special. You can already see that these are also fun problems. These are also fun. So, why these are fun properties? Why these lim soup and lim inf are something very interesting? Because